Okay, so in today's discussion, we will start off with probability theory. So whatever we have done is we have gone through the basics of credit risk modeling. We started with an overview of the domain. From there, we started talking about the different descriptive measures of statistics, the descriptive, the measures of dispersion, and finally what we did was we had discussed about the measures of asymmetry as well. From there we started framing an idea about how is it that a variable can be represented, or how is it that a variable can create a you know how is it that it can create a or these measures can help us create an idea or an insight about the behavior, about the distribution of a given variable, right? Guys, Anirudh, Piyush, can you hear me, guys? Am I audible? Okay. Okay. So in today's session, what we'll talk about is the concept of probability. Because when I talk about risk, right? So when I start talking about risk, risk is something which is about probability. So risk is something which creates a stochasticity in the cash flow of a bank. Risk is nothing but a lottery where there can be a good borrower. So when once I'm giving out a credit, there can be a good borrower, there can be a bad borrower. So a borrower can be a good or a borrower can be bad. I don't know. So there is always a chance associated with the outcomes. Therefore, what we need to do is, or what we need to understand from here is, we need to frame an understanding of the theory or the background or the guidelines which can help us in modeling risk. So any kind of uncertainty with whichever is attached with risk, right? So any kind of uncertainty whichever is attached with outcomes, so it is best modeled using probability. So where we know all the possible outcomes, but which particular outcome will occur in a given trial is not really known to us. And that is what is risk all about. So when I give the loan, I know that either I'll get the principal plus the interest back, or I may not get back anything, or a variation between the two. So at in the very high level, I may get back my loan, the loan that I have lent out, or I may not get back the loan that I have lent out, right? Hence, hence, from this perspective, we will talk about, and it is this from this perspective that we need to talk about theorization, about the probability theorization. And we start off with the very basic theory of probability, which is called the classical theory of probability, right? So, so just to start off with it. So the first thing topic that we start out over here is called the classical theory. Classical theory of probability. So what is the classical theory of probability? The classical theory of probability is the most basic and the simplistic framework based on which probability theory stands, on which which it was the first proposed theory of probability, and it lays the basics of the theory. It lays straight the basics of the theory. So now, when I talk about this, so what is classical theory? So the classical theory clearly states that if you have an event A, so I have an event A. So A is an event, or as we call it, an outcome, or as we call it, an outcome. So what I have is an event A, and I have an outcome. or what I call an outcome. Now, the probability that the event A will occur, the probability that the event A will occur is given by a very simple formula. So the probability of event A to occur is given by a very simple formula. That is the number of favorable outcomes to A. So the number of times, a number of outcomes that are favorable to the event A, number of favorable outcomes, right? The number of favorable outcomes divided by the total number of outcomes. Divided by the total number of outcomes, right? So when I talk about this, so let's look into some very basic examples. So one of the most basic example is the one that I started off with in the last class. Say I am suppose tossing a coin. So I'm tossing a coin, right? Now, if I'm tossing a coin, what are the possible outcomes that can happen in this case? So basically, there is a set of all the possible outcomes, which I call the sample space. So I know that if I toss a coin once, I'll get a head or I'll get a tails. So this is the set of all the possible outcomes, right? So this is called the sample space. So this S is called the sample space. So the sample space is the set of all the possible outcomes that are there, right? Now, having said that, the next part that we'll talk about is that so this sample space gives us the set of all possible outcomes. By looking into the sample space, I can say that okay, these are all the possible outcomes that this variable can or this experiment can have. Now what I want to do is I want to find out the probability of the respective outcomes. So one of the simple probability that I would like to calculate is the probability heads. So what is the probability heads? Now if we go by this given definition, the number of favorable outcomes divided by the total number of outcomes, what will you see? So over here, probability of head is nothing but uh, the number of favorable outcomes. So if I toss a coin, in how many ways can I get heads? Only one possible way, right? So the number of favorable outcome is 1 and the total number of outcomes is 2. Therefore the probability of head is half. Similarly, if I talk about the probability of tail, the number of favorable outcome is 1 and the total number of possible outcome is 2. So therefore the probability of tails is 2. I mean the total number of outcome is 2. Therefore, the probability of head and the probability of tail is half half each, right? So these are the respective probabilities that I have, and they have been calculated from this simple definition of classical theory. But now the question that comes out over here is that why is this called the classical theory, right? So let us answer that. Now, any theory is identified as a classical, modern, mathematical, whatever it is. So, a genre is identified from the set of assumptions on which it is based, or it is identified through the assumptions based on which it is, it is actually done, or it is actually formulated. So, having seen that, so let's see what are the assumptions, or what are the restrictions, or what are the conditions based on which this calculation has been made possible. Number one, the most important set of assumptions which has made this calculation possible is that the outcomes are discrete in nature. So the outcomes are discrete in nature. So this is discrete outcome. So this is where we get discrete outcomes. So the outcome of the random experiment is discrete in nature. So this is the first thing that, or this is the first assumption, the first condition under which the model is created. Now the next part is that the outcomes are discrete, and the second important criteria is the outcomes are finite in nature. So the next case assumption is outcomes are finite. So there are finite outcomes. Now after this, the next set of assumptions, the next set of conditions under which this calculation has been made possible is that the outcomes are mutually exclusive in nature. So the outcomes over here are mutually exclusive. So the third is mutually exclusive in nature. The next part that we have is mutually exclusive in nature. The next part is the outcomes are equally likely. All the possible outcomes are equally likely. Equally likely. Now observe that if any of these events or any of these assumptions fail, or if any of these assumptions are not satisfied, then it would become difficult for the team, or it would become really very difficult for people to subscribe, to this particular definition, right? So if your outcome was not discrete, had it been continuous, or had it not been finite, then this numerator and the denominator would not be defined. Hence what we can see is that even though the classical definition of probability has a very critical role to play over here, has laid out a very basic foundation for the concept of probability, but it has been done under certain assumptions. So it referred to a specific class of experiments, However, if any of these conditions were not satisfied, and we moved into another class of experiment which is very different from each other, then in that case it would be very difficult for us to understand. It would be very difficult for us to catch up with it. With this definition, it would become almost impossible for us to identify this distribution. Or I mean, it would become very difficult for us to apply this definition to compute probability. So, what are the different class of experiments where this can be done? And before we go into that, let us try to understand the concepts like mutually exclusive. What is mutually exclusive? So, two events are said to be mutually exclusive if and only if the occurrence of an event A forecloses the occurrence of event B. That is, if A occurs, then B cannot occur. And if B occurs, then A cannot occur. Right? So over here, so the events or the type of experiment or the type of stochasticity that this definition can help us in calculating probability is a very specific class of experiments. It's a very specific class of observation, specific class of frameworks. So what are they? So one such example we have already seen. That's a coin tossing example. Now another kind of this example would be the die rolling example, right? So there can be this die rolling example. So what happens in the die rolling example? So in a die rolling example, you are actually given a die and you roll the die. Die rolling. Die rolling case. So in a die rolling case, what happens is the sample space contains of 6 outcomes. S is 1, 2, 3, 4, 5, 6. Right? So this is a die rolling example. So over here we have 6 dies. I mean we have one die with 6 faces. So this is an unbiased die that we have. Right. Now having said that there is an unbiased die. Now what I want to know is that what exactly is the probability of getting each outcomes. Right. So what is the probability of getting one? So over here I want to know what is the probability of getting one. So if I roll the die once, what is the probability of getting one? So number of favorable outcomes. So if I roll the die, how many ways can I get one? There is only one possible way I can get one. And what are the total number of possible outcomes? The total number of possible outcome is 6. Similarly, if I want to draw this, I want to find out the probability of 2. So that probability is 1 by 6. Right? So similarly, what I'll again have is probability 3. So with probability 3, I'll again come up to 1 by 6. So this is the way, this is the way this entire thing would actually happen. So each of these events that you can see, so each of these outcomes have the same probability of occurrence, right? So probability of 1 is equal to probability of 2 is equal to probability of 3. equal to 3 and so on. So like this it will go on up to probability of 6. So you can see that the outcome or the chances of each of these outcome to occur is equal, and you cannot actually say that one event is more likely to occur than the other. So this is called equally likely events. Equally likely events. Equally likely events. Right? Now, if there is an equally likely event, right? So if I want to, if I want to know that, so that these events are equally likely. Also observe that if one occurs, then two, three, four, five, six cannot occur. If two occurs, then one, three, four, five, six cannot occur. If six occurs, then in any number between 1, 2, and 5 cannot occur. So it means that occurrence of one forecloses the occurrence of the other. Occurrence of two forecloses the occurrence of the other events. Therefore, this is called this is called the therefore this is called equally likely. Then the next is called the mutually exclusive events. Mutually exclusive events. Right? So is this idea of equally likely, mutually exclusive clear to everyone? And why is it called? So basically, what are the assumptions of classical theory? How is probability calculated under each of them? And what are the two key components of this mutually exclusive and equally likely? So is this part clear to us? Great. Now having said that, Kumar, now we need to understand that what are the feasible values that a probability may take. And whatever we have talked about, how is it that I can apply this basic concept of probability to risk? So let's first of all try and understand the value or the limits to probability. So basically, say, so there is a random experiment. So there has been some experiment, right, which has been conducted. So Anirudh has a question that when is probability cumulative in nature, right? So we'll come to that cumulative probability in a short while. Okay. So we'll come to that part. Okay. So let's say I have a sample space where this is A, B, C. Now the samples, there are multiple outcomes, right? So one is A, the one is B, the one is C, right? So obviously, just if you think about it, A has some occurrence, right? So A has some number of cases which is favorable to the occurrence of, say it is M1 or MA. So for B, similarly, B has number of cases favorable to the occurrence in B. Then this is MC. right? So there is MA, MB, MC like this, right? So over here, A, B, and C. So there are these three possible outcomes, right? And when I add them up, I'll get the total number of occurrences. Say when all these three are added up. Yeah, so M is the number of cases favorable to the occurrence of a given day, A, B, or C. So MA shows the number of outcomes which are favorable to the occurrence of event A. MB shows the number of outcomes which are favorable to the occurrence of B. Let MC shows the number of occurrences, the total number of occurrences favorable to the occurrence of C. So over here, so the number of cases are favorable to the occurrence of B. So it's MB plus MC. So obviously, MA is less than the sum of this value, right? So over here, what I can say is that if all these values are greater than 0, right, then this ratio is less than 1, but greater than 0. So probability of an outcome can never be negative. So either probability, so when I talk about probabilistic events, I'm talking about outcomes which have chances of occurrence between 0 and 1, right? Now after this, over here, the next part that we know is, say MA. So let us take the case where MB is equal to MC is equal to 0. Then the probability of A to occur is fully 1. So that is called a sure event. So if the probability of occurrence is 1, then it's called sure event. However, on the other hand, if MA is equal to 0, then the probability of A to occur is 0. If the probability of A to occur is 0, then this is called an impossible event. Impossible, right? So, right. So this is what the idea is. So basically, for probabilistic events, the probability lies between 0 and 1. However, if the probability is exactly equal to 1, then it's a sure event. If probability A is equal to 0, then it's an impossible event. Clear? So this is precisely the basic idea of probability. Up to this point, are there any questions? Anirudh, Preeti, Piyush, Prakash, anyone? Great. Because understanding this part of the concept is really very important. Because I know this is a very simple stuff that I'm talking about, but understanding this is again important because it is basis on this that the next parts would be built up. So having said that, the next part that we go on to talk about is that, okay, so this is what the idea is. Now we will start relaxing the assumptions. But before that, so we have seen that the probability is based on these four parts. The classical definition of probability is based on these four assumptions. One is a discrete outcome, the other is a finite outcome, the third is a mutually exclusive outcome, usually mutually exclusive event, and fourth is equally likely. Right? So this is what we have discussed. So this is what we know. And given these events, I can compute the probability. Now, let us first think about it that say suppose if the first assumption is violated, then what will happen? So for example, I say that either instead of having the sample space as h comma t or 1 2 3 4 5 and 6, what I have is a set S. I have a set S, right, which takes values between 0 and 1. Right, so this is where we'll talk about. So basically, now if you see that the sample space, it belongs to any number between 0 and 1. Right. Now the question that comes out over here is, so the question now that comes out is that what is the probability of getting 0.28? So what is the probability of getting 0.28? Now, if I try to use this definition, right? So if I try to use this definition, uh, then I would not be able to perhaps obtain this probability figure because I defining the total number of outcomes in the denominator or defining the total number of favorable outcomes is very difficult over here because there is 0.08. So this is what the probability figure is. Right now the discrete outcome is something which is not satisfied over here because there can be innumerable numbers between 0 and 1. Hence, if the nature of the outcome changes, right, so if the outcome set becomes continuous in nature, if this becomes continuous in nature, if this becomes continuous in nature, then then this definition would not apply. So in that case, we would require some other techniques, right? So we need to understand that how much of or like what is the total length, or say what is the total thing, and how much is it that we are actually looking into, right? So over here, one very simple way. So let's see how is it that we can do that. So let's just try to do this graphical. I'll draw this graph. So over here, so say this is 0 over here, and there is 1. And over here is 0.28. So this is the probability of point, right? So over here, what I want to know is, so in this case, so if I have this kind of a continuous function, right? So instead of identifying what is the probability of getting 0.28, it is always better to understand the probability of what is the chances of getting a probability less than equal to 0.28. So over here, what we are trying to do is we are trying to understand that what is the probability that this variable will take a value less than equal to 0.28. So over there, the probability of getting this probability or to computing this probability is, so the total number of favorable events will be what? It will be the length of the line segment between this 0.28 and 0. So it is 0.28 minus 0 divided by 1 minus 0. So therefore, the probability of getting probability of getting x less than equal to 0.28 is 0.28, right? Right. So what we can see is the moment one of these assumptions changes from discrete to continuous, this conventional definition of m by n does not work over here. So this is one of the most important limitations of the classical theory. Now suppose the outcome is discrete, right? So let's take it the outcome is discrete, but the set is not finite. So if it is an infinite set of outcomes, then the total set of outcome becomes infinite. Then the denominator becomes undefined. And when this happens, the probability cannot be computed properly. So I cannot get a clear idea about how what is the defined value of the probability. So that is the second limitation over there. Now again, this function or this particular framework, the classical theory framework, is only valid for cases where the events are mutually exclusive in nature. So this definition that you have framed over here, I mean that we have framed over here is based on the assumption that the events are discrete in nature. It does not, so this event cannot, or I mean this description cannot work if the events are not mutually exclusive in nature, right? Now after this there is, so let's try to understand, right, that how would it or how does this thing actually grow. So for example, there are two candidates, right, candidate A and candidate B, who appear for an interview. So sorry, yeah, let's start. So basically, just say let's take the case of two candidates, right? So there is candidate A and there is candidate B and there is candidate C, right? Now I want to know. So all the three have these three people have appeared for their interviews, right? Now, given that they have appeared for their interviews, the next thing that happens over here is that there are two vacancies. So these three candidates have arrived or have come up for an interview for two vacancies. So there are these two. So basically ABC. So these are two vacancies. Now I want to know that what are the probabilities of A and B to crack through. So basically, uh, say I want to find out the what is the probability that A and B gets through or gets the job, where both A and B have their individual probabilities of cracking the interviews, which may not necessarily be, you know, which may not necessarily be, uh, what should I say, which need not necessarily be uh, equally likely. So, say for example, even the probability of individual candidate A to get the job is 2/3, right? That of probability B is say 1/6, right? And that of probability C is 1/6. So these are the three probabilities of the individual to get through, right? Now, what I want to know is what is the probability of A and B. So what you see is that these three events or these three outcomes are not necessarily mutually exclusive. A getting the job does not foreclose from B and C getting the job. Probability of B getting the job does not stop A and C from getting the job. So this assumption of mutually exclusive behavior is violated in this case. Hence, it becomes impossible. Hence it is not possible to use this particular definition for further usage. So the classical theory of or the classical definition can only be applied to events where there is discrete outcomes, finite, mutually exclusive, and equally likely outcomes. So if any one or more of these assumptions are violated, then you cannot do anything about it, right? Okay, I'll just come across again. So over here, PT, what it says is that there are say three candidates, right? A, B, and C, who are applying for two vacancies in an office. Now, if A gets through, that does not necessarily mean that B or C cannot get through. On the other hand, if B gets through, that does not again mean that A and C cannot get through. Therefore, the outcomes that I get to see over here are not mutually exclusive, right? However, so if you use the classical theory to compute this, you would not be able to compute because the outcomes are not mutually exclusive, but rather there is a new type of an event which has come up through this kind of a problem. That event or that type of event is called the set of independent events. Now it can be that both A and B are independent in nature. So A getting through the job and B getting through the job are absolutely independent in nature. So over here we can have a new set of events called the independent events. Now independent events are something which cannot be modeled as a part of the classical theory. And that is where the next strand of economic theorization comes in, which is called, so basically over here what happens is, so to get to each of these cases or to model these cases, we develop a new strand of theory, or we look into a newer branch of probability theory, which is called the mathematical probability theory. Now before I move into that, I'll take up a question which Anirudh has. And it says that but here how probability has been calculated. Okay, so over here for the probability A, B, and C, these probabilities have been perhaps calculated, can be calculated, using this classical theory or this classical definition, because say I see that out of every three jobs that he has applied, right, Anirudh has had, this guy has had the talent to crack two jobs. Therefore, his probability of cracking the interviews or a representative interview is 2,000. So that probability can be calculated by classical theorization, right? So number of jobs applied and number of jobs cracked. So that gives you this probability. So A, B, and C perhaps can be calculated by classical method, because you either get the job or you don't get the job. So number of times you have applied for a job, the number of times you have cracked through. So that gives you your probability. So this probability A, B, and C that I have calculated over here, that does satisfy the assumption of the classical model. But when I take it up one step forward, and I try to understand that when these three guys are applying for an interview, right, and they have their respective probabilities of cracking through that, then what is the probability that A and B class, A and B qualify together for that interview? So when I try to take up this kind of a problem, I see that the classical theory does not make much of an impact, right? So to solve this kind of a problem, or to solve these kind of problems, we have an advancement of classical theory, which is called the axiomatic theory of probability. So the next theory that, before going into mathematical theory, the next theory that we talk about over here is the axiomatic theory of probability. So the axiomatic theory of probability comes before the mathematical theory of probability, right? But this succeeds the classical theory. But again, the axiomatic definition has a problem, that it is not really applicable for continuous variables or for experiments which have continuous outcomes. Axiomatic outcome again is very discrete in nature, but it helps us in solving a way out of the last two problems, mutually exclusive and equally likely. But again, it would fail if the events are not discrete and finite. So the next is the axiomatic definition of probability. So the axiomatic definition becomes useful when I want to know that whether two whether two events are likely to occur together. So is it possible that two borrowers A and B default together, or two groups of borrowers or two types of borrowers default together, where the probability of group A to default is this and probability of B to default is this? So if we are looking to that kind of a problem, if we look towards that kind of a problem, that is where this axiomatic definition becomes handy, right? So we'll first explore some basic portions of axiomatic definition, and the objective of for exploring the axiomatic definition is not to look into its formulas, but to bring into but to explore one specific kind of an event, right? And that event is called independent events, and to explore the difference between independent events and mutually exclusive events. So the contribution of the axiomatic definition is that it's an extension of the classical approach and helps us in generalizing the concept of probability to incorporate non-mutually exclusive and unequally likely event as well, right? So previously, all the outcomes that we had talked about, all the events or whatever the sample space have been constructed, so we saw that all the events are equally likely to occur, but there can also be events which are not equally likely to occur. So how do you capture those? So those are captured using the axiomatic definition, right? Okay. So the next part that we talk about is axiomatic definition. So when I talk about the axiomatic definitions, so okay, so before I move into axiomatic definition, so is this idea clear to you, Priya? Is that example that I was talking about, is that example clear? Okay, so Anirudh, what is not clear in that example? What are you not clear about? First, let's clear that part and then we'll move ahead. What is not clear in this example? Which portion? Okay, okay. Okay, so this probability A, B, and C, these values I have written arbitrarily, right? So these are just examples. So I've just done it under the assumption that A is twice as likely to get the interview compared to B and C. So B and C are equally likely events, but A has a different probability. A has a chance. A is twice as likely to get to crack through the interview. So this is just an example. So this has no calculations involved with it, but this is just a priori given value. That's it. The two values have been kept the same, right? To demonstrate that even the mutually exclusive, but the third has a different probability altogether. Okay, so over here, since there are three probabilities, or since there are three outcomes, okay, so you would see that, okay, hold on, you would see that two-third, right? So this probability is two-third, right? So the probability of A to crack through the interview is two-thirds. So this is what we have calculated from somewhere. This is just a value. That means chances of the other three people, I mean the other two, must be what? How much? One-third, right? So if A has a probability two-third of cracking the interview, the other two added up must have one-third. So what I have done is I have divided them purposely by 6, so half. So each of the borrowers have, or I mean each of the interviewers have, the candidates have 1 by 6 and 1 by 6 chances, right? So if I add all the three up, I'll get. So if there are these three candidates who are applying, then at least one of the three candidates must get the job, right? So when I add the three up, you will see that they always add up to 1. So this is just an arbitrary value which I have actually shared. So there is no calculation involved in it. These are just arbitrary a priori given values. That's it. Great. Say for example, I'll bring this more, I'll make it more relevant over here. Say suppose, as a bank, what I have done is, so before going into the axiomatic definition, so over here as a bank, right? So there is this bank. So as a bank, what I've done is I've given out credit to these three people. So I've given out credit to three people or to three candidates, to three borrowers, right? A, B, and C, right? So I've given out the credit, and now what I've been doing is I have been monitoring the behavior of these customers over time, right? Now, at the beginning of the year, what I do is, at the beginning of every year, I run a PD model, right? So I always run a PD model on these customers and calculate the probability to default. So basically, so since these are customers who are on my books, what I try to do is what I'm essentially doing for all these three customers or for all these three borrowers is I'm doing an account management exercise. So I manage the accounts of each of them, and I track how much are they spending on the credit, how much have they used the credit product. Okay, so how much are they paying back, whether they are paying back regularly or not, what is, are they paying back every time on the due dates, or are they delaying or they deferring the payment, are they missing out on payment, and so this is what I actually do. So this is what is account management, right? So one very important part of account management is that I try to, so one part of account management is, what I try to do is I try to frame an understanding of whether these borrowers have chances of defaulting or not. So what I'll do is what I try to always understand is that there are these borrowers. So there are two possibilities: either the borrower remains good or they default. So y equals to 1 if the borrower defaults in the next 12 months. If the borrower defaults in next 12 months. So if the borrower is defaulting in the next 12 months, then or if a borrower defaulted in next 12 months, I'll flag him as 1, else I'll flag him as 0. 0 otherwise. So say suppose I am a borrower who is standing today. So both A, B and C are standing today, right? So both of them are standing, all these three are standing as on 24th March. So they are standing as on 24th March, right? So I have my own PD model, right? And I run all the PD with the PD model on all these three borrowers. So what I'll get is their chances to default in the next 12 months. So I'll be able to estimate that as on standing today, over the next 12 months, what is their probability of defaulting. Right now, this probability of defaulting will be obtained from a model. So this will be obtained from the PD model. PD model, right? Now, once I have this, so this will give me what? A probability of y equals to 1 for A. So I'll get the probability of A to default, so which is some value P0. I'll get the probability of B to default, which is some value P1. How these probability estimates are generated from these for these probability default models, that is something we will discuss when we are talking about probability of defaults, right? So then again I have probability of C, right? So these are the estimated probabilities that I have got. Now what I want to know over from here, from this data is, or from this model is, that what is the probability that A and B to occur. So what is the probability of A and B to occur? I mean, what is the probability that A and B will default, right? Now A and B are two independent obligors who have taken the loan. So I need to know that what is the probability that A is defaulting and B is defaulting. So to find that out, we can say that it is probability of A intersection B, which is equal to A dot probability B. Given that both A and B, given that both probability A and B are, I mean, given that A and B are independent events. So A and B are independent, right? So suppose now over here I am seeing that. So or I want to know that what is the probability that exactly two borrowers might default out of the three. What is the probability that exactly one borrower will default out of three? So these are different things that we may want to investigate once we have all the probability estimates, right? So over here, what we are trying to do is we are trying to frame an understanding of the applicability. Now, if I were to find out this A and B, now if A and B, if I'm trying to calculate the probability of A and B together, then obviously I'm violating the mutually exclusivity of assumption. So if given that the mutually exclusive assumption is violated, we cannot do it using this characteristics, right? So therefore, we need to bring in the axiomatic probability theory. So the axiomatic probability theory helps us to calculate the probability for events which are non-mutually exclusive in nature, which are non-independent or independent, non-independent, etc., which are non-equally likely in nature, etc. So for doing all these, the extension to the classical theory that was done was the axiomatic definition. So is it clear now for the reason for why we are to study the axiomatic behavior? I mean the axiomatic probability definition. Sit down and think over this example for the next 2 minutes, and then we will start off. Okay, so is this idea clear? Great. So with this, we move into the next form. Okay, so let's move on. Okay, just a quick thing, guys. Just do refer to this YouTube channel, and you can get all these recordings up over here. Okay, so the next part that we'll talk about over here is the axiomatic theory, the axiomatic probability theory. So the advancement or the contribution that axiomatic theory had in over here was that it helped to generalize the type of the events from mutually exclusive and equally likely to independent events, non-mutually likely, or I mean non-mutually exclusive and events which were not equally likely, right? So that is where this axiomatic definition comes in. Axiomatic definition. So in an axiomatic definition, what we said or what they said is that so the axiomatic definition lays out the probability expressions or probability rules for mutually exclusive events as well as non-mutually exclusive events. Events and for non-mutually exclusive events or normal events. Right. So, so over here, what we have is mutually exclusive and non-mutually exclusive events. So, how does or what are the the rules or what are the formulas that axiomatic definition lays out? Now, to understand this mutual, to understand this framework, we need to have a good understanding of the set theory as well. We need to have a clear cut understanding of what these symbols mean and what are the basic, uh, what do the basic symbols mean, like union, intersection, A complement, only A, only B, like these. So these are something that we need to understand. So so let's just have a quick look into set theory. So over here, let's create a set A, and then let's create a set B. So this is a case where you do not have, or which is not a non-mutually exclusive, which is a non-mutually exclusive event, right? So and you have an overlap between A and B over here. On the other hand, what we have is event A and event B, right? So over here, so this was this red part that we saw over here. This was purely your classical case. This was purely the classical case. So over here, so let's look into this thing first. So this part that I get to see over here is this part that we get to see over here is A intersection B. So what do I mean by A intersection B? A intersection B means the part which is common between the two sets A and B. So this part talks about A and B, right? Okay. So this shows A and B. Similarly, if I look into this part, this entire part, so this is called the A union B. So this part talks about A or B, right? So these are the two most important things that we need to talk about. So however, if we are talking about A union B, you will see that there is this A intersection B which is also falling in between, and hence this is the part which needs to be adjusted, right? So this is A intersection B and the other is A union B. So these are the two important things, and hence when we are computing the probability, right, this needs to be taken into account. Now let's take look into another part of this set. So another part of the set is this part, only A. This part is called only A. Only A. But given that this is only A, so what do you mean by only A? Only A means elements which are in A but not in B. So over here what I have is B intersection or B complement intersection A, or A intersection B complement as we might call it. So this shows elements in A but not in B. Elements in A but not in B. Elements in A but not in B. Right? Similarly over here, and this is also known as only A. So if you want to know only A, when A and B, when there is an overlap between A and B, you also need to adjust. You are only looking into that part of A which is solely in A but not in B. So this part is called only A. Similarly, if you look into this part, only B, look into this part. This part is nothing but B intersection A complement, right? Or as we can call it, only B. Now you can clearly see that this part that we have labeled over here is something which is not a part of the classical definition the way we had said it. So basically the events that will happen over here are not mutually exclusive. They can be non-mutually exclusive as well. So where both A and B can occur, A or B can occur, only A can occur, only B can occur, right? So from this framework of the set theory, right? From this framework of the set theory, the axiomatic definition draws its conclusions. So the first conclusion that it draws is for mutually exclusive events. It says that if there are n events which are mutually exclusive, right? If there are n mutually exclusive events, if there are n mutually exclusive events, then probability of I want to do AI is equal to how much? Is equal to probability of E1 union E2, which is probability E1 right? So this is where we are talking about. So probability union I want to do AI is equal to A1 union A2, which is summation probability AI. So this is for non-mutually exclusive events. So it says that if two events are mutually exclusive, then the union of the probability of the union of two events is the summation of the probability of the two events. So this is where this is what even your classical theory also would say, and it would focus only on this group of events. Now the contribution of the axiomatic definition is, just give me a second. Hey, hi guys. Okay, okay, great. So, Anirudh, to your question, please give an example in terms of banking. So, we'll not immediately bring in banking over here. What we are trying to do is we are trying to understand the concept of sex, and then from there, once this part is done, I'll give an example on banking. Right. So, to refer to this, to refer to this concept, if you want to relate it to this, what you need to do is you just need to look into this group of into this example, right? So there is probability A, there is probability B, and there is probability C of three of these borrowers. Now if I want to know that what is the probability of A and B to default, so A and B are independent over here, right? So basically over here we'll talk about, so over here we are just talking about the mutually exclusive events, right? So there are two people, right? A and B. So what is the probability that A or B can default, or the default can happen from segment A or from segment B? So this is what we are trying to do. Right. So over here we are just trying to create. We are just trying. I'm just trying to create the theoretical framework first. Then I'll bring in the examples from banking. Right, because there are a lot of these different concepts going in today. That's why I'm not bringing in the examples. So once we understand the difference between these two approaches, then we'll focus more on examples, because to get to the real-time banking examples we need to get into distribution first. So once we get into distribution, over there we will be able to identify a better example, a better kind of case for development. Okay. Okay. So for non-mutually exclusive events, how will this union look like? So over here, when I'm looking into the union of the two events, so what I'm trying to do is I'm trying to understand this I equals to 1 to 2 AI. So this is the probability that event A or B can happen, right? So basically, let's take that event A is that there is an application which is coming in, right? Now every application can be accepted or declined, right? So they are either accepted or declined. Now within being declined, right? So there are two possible declines that can happen. One is a score decline. So basically the score of the application score is lower than the cutoff score. The application is decline. The second is policy decline. Now within policy decline there can be multiple categories. So basically one way I can look into say is that, okay, so this given that this application is coming in, what is the probability that it will be policy decline due to demographic regions, or policy decline due to income regions, income levels. So whenever I'm trying to find out the probability of A or B, so either this flaw is happening because of A, or is happening because of B, or is happening because of C. So when this or comes in, that is where this question of that is where this question of A union B comes in. Now let's think about, so we saw that for a mutually exclusive event. If the event was not mutually exclusive, using the definition of classical theory, it was not possible for us to calculate the probability if the event was not mutually exclusive. So what we do is we extended this to the axiomatic definition, and let's see how that problem is solved. So over here what I have is A, and over here what I have is B. Now let me start off with the part that I'll keep it at probability A plus probability B, right? So if I have probability A over here, so probability A over here will be this part. The A is this part, and probability B is again this part. So what you see is that there is an overlap, right? So there is an overlap which is being created. So therefore this A intersection B is being recorded twice, or is being double counted. Is being double counted, right? There is A intersection B, and this is being double counted. So over here what will happen is, so this one of these values needs to be removed from here. So that is minus probability of A intersection. So probability A union B is A probability A plus probability B minus the probability of A intersection B. Clear? So with this formulation, when we are referring it to set theory, when we are bringing in the set theory and we are trying to estimate the probabilities, then I can see that it leads me to a more generalized framework, right? Clear, everyone? Great. So what we'll do is we'll stop here for the day. I'm sending over this board work to you, right? Just go through it before tomorrow's session. I'll just send over the board work to you right now. Just go through the concepts, see whether is there any challenge in understanding anything, and then we'll start off with the mathematical probability theory tomorrow. And by tomorrow, I'll upload the recording of this session into the YouTube channel. Okay, so that you can access it directly from there. I hope you would not be having a problem accessing it from there, right? So I shared the link. So just subscribe to the channel and then you can directly go about it. And if you know your friends who are interested in going through the videos and anything, please tell them to subscribe it as well. And it's absolutely free, so there is no challenge. But when I start off with the coding part or the technical part, those will not be featured in YouTube, uh, because these are exclusive materials, and that there has been a financial involved at your end as well, and hence it would not be made free. But since these are basic generic stuffs, and okay, so I'll just share this with you, and then we'll just close the session. Thank you, guys. See you tomorrow. So, tomorrow we meet at 2, and then we'll take it up from there. Thank you. Bye bye.